Welcome to today's paper reading. Today's paper is titled, A Survey of Prompt Engineering Methods in Large Language Models for Different NLP Tasks. This paper was published on the AR14 preprint by Shubham, Vatsal, and Dubey from the Department of Computer Science at New York University. Large language models, LLMs, have demonstrated exceptional performance across various natural language processing, NLP, tasks. A critical aspect of enhancing these models' capabilities is prompt engineering, which involves composing natural language instructions to elicit structured knowledge from LLMs. Unlike previous state-of-the-art models, prompt engineering does not necessitate extensive parameter retraining or fine-tuning, making it accessible to individuals without a deep machine learning background. This paper reviews different prompting techniques, categorizing them by the NLP tasks they are applied to, and discusses their performance on various datasets. The study encompasses a survey of 44 research papers, detailing 39 distinct prompting methods across 29 NLP tasks, most of which have been published within the last 2 years. The introduction of large language models, LLMs, has significantly advanced the field of artificial intelligence. These models, trained on vast corpora of text documents, have shown that as the number of model parameters increases, so does the performance of machine learning models. LLMs have achieved unprecedented performance on a wide array of NLP tasks, attracting interest from academia and various industries such as medicine, law, and finance. The current focus of research on LLMs is on their reasoning capacity via prompts, which has opened a new field of research around prompt engineering. Prompt engineering is the process of creating natural language instructions to extract knowledge from LLMs in an organized manner. Unlike earlier models, it relies solely on the embedded knowledge of LLMs and does not require extensive parameter retraining. This new field has caught everyone's attention as it allows natural language exchange between researchers and LLMs to achieve the goals of the underlying NLP task. In this work, the authors enumerate several prompting strategies and group them according to different NLP tasks. They provide a taxonomy diagram, tabulate the prompting techniques tried on various datasets, discuss the LLMs employed, and list potential state-of-the-art methods for each dataset. The survey reviews and analyzes 44 research papers, the majority of which have been published in the previous 2 years and cover 39 prompting techniques applied on 29 different NLP tasks. This section discusses various prompting methods and their impact on performance improvements. The main variations include zero-shot and few-shot settings. In zero-shot, no training data is used, relying solely on the model's pre-trained knowledge. In contrast, few-shot involves providing a few training examples to better understand the task. Key prompting strategies include chain of thought, COT, which breaks down complex problems into simpler subproblems, showing significant improvements in mathematical and common-sense reasoning tasks. Self-consistency uses multiple reasoning paths to find the most consistent answer, achieving notable gains in mathematical and common-sense reasoning. Ensemble refinement, ER, builds on COT and self-consistency, showing better performance across various tasks. In this section, we standardize the categorization of datasets under various NLP tasks. We define different NLP tasks and assign datasets to these tasks based on their strong association. We also discuss various prompting methods used for these tasks, noting that the performance of these methods can vary depending on the language model used. Our approach ensures that each dataset is assigned to only one NLP task to avoid complex entanglements in performance analysis. Figure 1 presents a taxonomy diagram that categorizes various prompt engineering methods across different NLP tasks. The diagram highlights key methods such as chain of thought, COT, random COT, and complex COT for mathematical problem solving, basic program-aided language models, PAL, and synthetic prompting for logical reasoning, and contrastive COT and contrastive self-consistency for common-sense reasoning. This taxonomy helps in understanding the application of these methods across a wide range of NLP tasks, providing a structured overview of the current state of prompt engineering techniques. Table 1 provides a detailed analysis of various prompt engineering strategies applied to different datasets in the context of mathematical problem-solving tasks. Key datasets include GSM-8K, Math, and SVAMP, each showcasing different prompting strategies such as pattern exploiting training, POT, analogical reasoning, and contrastive self-consistency. The table highlights the best-performing prompting methods for each dataset, offering insights into the effectiveness of different approaches in enhancing the performance of large language models, LLMs, in mathematical problem-solving scenarios. Table 2 provides an analysis of the prompt engineering strategies used for the logical reasoning task. It lists various datasets such as word sorting, logical deduction, and temporal sequences, along with the prompting strategies like basic, analogical reasoning, COT, and COC. The table also mentions the large language models, LLMs, used, including GPT 3.5 Turbo, GPT-4, Palm 2L, and Palm 2S. This analysis helps in understanding the best-performing prompting methods for each dataset in the context of logical reasoning tasks. Table 3 provides an analysis of various datasets used in the common sense reasoning task, detailing the prompting strategies and the best-performing large language models, LLMs. Key datasets include reasoning about colored objects, CSQA, and date understanding. The table highlights the use of prompting strategies such as basic, COT, AutoCOT, and self-consistency. Notable LLMs include Palm 2L, GPT 3.5 Turbo, GPT-4, and UL2-20B. This analysis is crucial for understanding the effectiveness of different prompting methods in enhancing the common-sense reasoning capabilities of LLMs. Table 4 provides an analysis of prompt engineering strategies for the multi-hop reasoning task across various datasets. Key findings include the use of active prompt for strategy QA, CoQ for hotpot QA, and DecumP for comma QA. These strategies represent the best-performing methods in their respective datasets, highlighting the effectiveness of specific prompting techniques in enhancing multi-hop reasoning capabilities. Table 5 provides an analysis of the prompt engineering strategies used for the causal reasoning task. It includes datasets such as cause and effect and causal judgment, and lists various prompting strategies like basic, COT, COC, and LOT. The table also mentions the LLMs used, including GPT 3.5 Turbo, GPT-4, Vicuna 7B, and Palm 2S. Table 6 provides an analysis of prompt engineering for the social reasoning task using the social QA dataset. The table highlights the prompting strategies of chain of thought, COT, and language of thought, LOT, and lists the large language models, LLMs, tested, including GPT 3.5 Turbo, GPT-4, and various Vicuna models, 7B, 13B, 33B. This analysis is crucial for understanding how different prompting techniques and LLMs perform in tasks that require reasoning about human social interactions. Table 7 provides an analysis of prompt engineering strategies for the contextual question answering task across various datasets. Key datasets include ProcessBank, BioMRC, and MashQA, each tested with prompting strategies such as basic, implicit RAG, chain of thought, COT, and analogical reasoning. The table highlights the best-performing prompting techniques for each dataset, aiding in understanding the effectiveness of different strategies in contextual QA tasks. Table 8 provides an analysis of prompt engineering strategies for the context-free question answering task. It lists various datasets such as PopQA, EntityQ, and Wikidata, along with the prompting strategies like basic, COT, and thought that have been experimented on them. The table also highlights the best-performing prompting strategy for each dataset. Additionally, it mentions the large language models, LLMs, used, including GPT 3.5 Turbo, GPT-4, and Llama 2 series, which are crucial for understanding the effectiveness of different prompting techniques in context-free QA tasks. Table 9 provides an analysis of prompt engineering for the spatial question answering task. It includes datasets like Brick World, and LVR-based manipulation, and natural language navigation, among others. The table details various prompting strategies such as COT, COS, and BASIC, along with the best-performing large language models, LLMs, including GPT 3.5, GPT 3.5 Turbo, GPT-4, and Palm 2S. This analysis helps in understanding the effectiveness of different prompting methods on spatial reasoning tasks. Table 10 provides an analysis of prompt engineering strategies for the conversational contextual question answering task. The dataset used is CONV-FINQA, and the prompting strategies include POT, COT, self-consistency, and PAL. The large language models, LLMs, involve our codecs, GPT-3, GPT 3.5 Turbo, CodeGen, Code T5 Plus, SGen, PaLM, and Lambda. This table highlights the best performing prompting strategies for enhancing the model's ability to answer interconnected queries in a conversational format. Table 11 provides an analysis of prompt engineering strategies for the dialogue system task, focusing on the multi-turn conversation response, (NTCR) dataset. The table lists various prompting strategies such as basic, chain of thought, COT, and thought, and the corresponding large language models, LLMs, including GPT 3.5 Turbo, Llama 2 models, and Vicuna. This analysis is crucial for understanding the effectiveness of different prompting techniques in enhancing the performance of dialogue systems. Table 12 provides an analysis of prompt engineering strategies for the code generation task. It lists datasets such as code force scraping, human eval, MBPP, and MBCPP, along with various prompting strategies like analogical reasoning, chain of thought, COT, and self-consistency of thought, SCOT. The table also mentions the LLMs used, including GPT 3.5 Turbo, GPT-4, PaLM 2L, and Codex. This analysis helps in understanding the best performing prompting techniques for generating code in different datasets. Table 13 provides an analysis of prompt engineering strategies for the free response task. It highlights the datasets used, which include creative writing and long-form generation of biographies. The table lists various prompting strategies such as basic, COT, self-consistency, and TOT. Additionally, it mentions the LLMs involved in the experiments, including GPT-4, Llama 65B, and Llama 2-70B chat. The table aims to identify the best techniques for generating unconstrained textual responses. Table 14 provides an analysis of prompt engineering techniques for the truthfulness task across various datasets. The datasets include sycophancy eval, fever, and GSMIC. The prompting strategies evaluated are S2A, COT, and instructed prompting. The leading language models used in these experiments are Llama 2-70B chat, PaLM 540B, and GPT 3.5. This table highlights the best performing techniques for ensuring factual communication without misinformation. Table 15 provides an analysis of prompt engineering strategies for the table-based truthfulness task. The dataset used is TabFact, and the prompting strategies include basic, COT, binder, dater, and chain of table. The models evaluated are PaLM 2S, GPT 3.5 Turbo, and Llama 2-17B chat. The best performing strategy identified is chain of table. Table 16 provides an analysis of prompt engineering strategies for the table-based question answering task. It includes datasets like WikiTQ and FATAQA, and evaluates various prompting strategies such as basic, chain of thought, binder, dater, and chain of table. The table also lists the large language models used in the experiments, including PaLM 2S, GPT 3.5 Turbo, Llama 2-17B chat, and Codex. The state-of-the-art SoTA prompting strategy identified is chain of table. Table 17 provides an analysis of prompt engineering strategies for table-based mathematical problem-solving tasks. It covers two datasets, TabMWP and Penguins in a table, and lists various prompting strategies such as POT, COT, self-consistency, and PAL. The table also includes the large language models, LLMs, used in the experiments, including Codex, GPT-3, GPT 3.5 Turbo, CodeGen, Code T5 Plus, SGen, PaLM, and Lambda. Table 18 provides an analysis of prompt engineering strategies for the recommender system task, specifically focusing on the movie recommendation dataset. The table lists various prompting strategies such as basic, chain of thought, COT, and chain of context, COC, and identifies the best performing technique as POT. This table is crucial for understanding the optimal prompting methods for enhancing recommender system performance. Table 19 provides an analysis of prompt engineering strategies for the emotions/sentiment understanding task. It includes datasets like snarks, ruin names, semival 14, and 4x, and evaluates prompting strategies such as basic, cot, cock, and thor. The table also lists the large language models, LLMs, used in the experiments, including Palm 2s, GPT 3.5, Flan T5, and GPT-3. Table 20 provides an analysis of prompt engineering techniques for the machine translation task. It includes datasets such as salient translation error detection, FLORES, WMT21, multi-domain, and PDC. The table lists various prompting strategies like basic, cot, cock, and basic plus variations, and the corresponding large language models, LLMs, used, including Palm 2s, GPT 3.5, GLM 130B, and Thor. This analysis helps in understanding the best performing prompting strategy for each dataset in the context of machine translation. Table 21 presents the analysis of prompting strategies for the named entity recognition (NER) task across various datasets. The datasets include MT samples, VIRS, research papers, and BC5 CDR Chem. The prompting strategies evaluated are basic, annotation guideline-based, and error analysis-based. The LLMs used in the experiments are GPT 3.5 Turbo, GPT-4, Llama 2-13B Chat, and PaLM Bison Chat. This table highlights the best performing prompting strategies for each dataset in the context of NER. Table 22 provides an analysis of prompt engineering for the word sense disambiguation (WSD) task. The WIC dataset is utilized, and various prompting strategies such as chain of thought, COT, prompt shifting, PS, self-consistency, and model parallelism, MP, are explored. The analysis includes performance data from several large language models including Llama 2-13B Chat, GPT 3.5 Turbo, GPT-4, and PaLM Bison Chat. Table 23 provides an analysis of prompt engineering for the summarization task, focusing on datasets WCP and CCDC. The table lists the prompting strategies used, which include BASIC and COE, and the language models involved, specifically ChatGLM 2-6B. This analysis helps in understanding the best performing prompting strategies for summarizing lengthy texts into concise chunks while retaining essential information. Table 24 provides an analysis of prompt engineering for the paraphrasing task, detailing the datasets used, prompting strategies, and the language models involved. The datasets include QQP and SoTA, with prompting strategies such as chain of thought, COT, prompt source, PS, self-consistency, and model parallelism, MP, being employed. The language models tested include Llama 2-13B Chat, GPT 3.5 Turbo, GPT-4, and PaLM Bison Chat. Table 25 provides an analysis of prompt engineering for the stance detection task, focusing on datasets like SemiVal 2016, VAST, and PStance. The table highlights the use of the chain of thought, COT, prompting strategy across these datasets, with GPT 3.5 Turbo as the primary language model utilized. This approach aims to evaluate the model's ability to determine the stance of the author on a given topic, whether in favor, against, or neutral. Table 26 provides an analysis of prompt engineering strategies for the natural language inference (NLI) task. It covers two datasets, QNLI and MED-NLI, and evaluates various prompting strategies including chain of thought, COT, prompt shifting, PS, self-consistency, and majority voting, MP. The table lists the large language models, LLMs, used in the experiments, such as Llama 2-13B Chat, GPT 3.5 Turbo, GPT-4, and PaLM Bison Chat. The best performing prompting method is highlighted for each dataset. Table 27 provides an analysis of prompt engineering strategies for the relation extraction task, focusing on the DDI dataset. The table lists various prompting strategies such as chain of thought, COT, prompt shifting, PS, self-consistency, and multiple prompts, MP, which have been tested with large language models including Llama 2-13B Chat, GPT 3.5 Turbo, GPT-4, and Parlem Bison Chat. The best performing strategy identified is multiple prompts, MP. Table 28 provides an analysis of prompt engineering strategies for language-based task completion. It covers 4 datasets: ALF World, Scan, Web Shop, and SACAN. The table lists various prompting strategies such as ACT, React, Basic, COT, and Least to Most, which have been experimented with on these datasets. Additionally, it mentions the LLMs used, including Palm 540B, GPT-3, Codex, Lambda 137B, and UL2-20B. The table highlights the best performing prompting method for each dataset, offering insights into effective strategies for language-based task completion. Table 29 presents an analysis of prompt engineering strategies for the multi-label text classification task across 3 datasets: EuroLEX, Unfair to Us, and Ledger. The table lists the prompting strategies experimented with, including chain of thought, COT, prompt source, PS, self-consistency, and model predictions, MP. The best performing models for these strategies are also noted, such as Llama 2-13B Chat, GPT 3.5 Turbo, GPT-4, and Parlem Bison Chat. This table is crucial for understanding the effectiveness of different prompting methods in multi-label text classification tasks. Prompt engineering is essential for large language models, LLMs, as it helps in realizing their full potential. In this study, an in-depth survey of 44 research papers was conducted, focusing on 39 different prompting strategies applied across 29 natural language processing (NLP) tasks. A taxonomy diagram was created to visually represent these strategies. Additionally, the categorization of datasets into 29 NLP tasks was standardized, and the overall impact of recent prompting techniques was discussed. The study also identified potential state-of-the-art SoTA prompting methods for each dataset. Thank you for watching.